In this video, I'm going to show you some examples about finding integral of rational functions with the partial fraction decomposition method. The first example is integral of x plus 6 over x to the 2 plus 3x dx. We have a rational function, a polynomial in the top, a polynomial in the bottom. First, we have to rewrite this expression x plus 6 over x to the 2 plus 3x in terms of partial fractions. First, we factor the denominator. The first step in writing a rational function in terms of partial fractions is always to factor the denominator. Simply we can factor x and then we have x plus 3. And we leave the numerator. And of course, you have to always check that the degree of numerator is less than the degree of denominator. The degree of numerator is 1, the degree of the denominator is 2, so we don't need to do any long division first. And right away, we start writing the partial fraction decomposition form. For this expression, we have two factors in the denominator, x and x plus 3. And in the numerator, we put the coefficient, the unknown coefficients as usual, a and b. If you are not familiar with how to write a rational function in terms of partial fractions, please watch my other videos in this regard. For finding values of a and b, we are going to multiply left side and the right side of this equation by this denominator. The reason that we do this is that we want to get rid of the denominator. So we are going to multiply left side and the right side by x times x plus 3. So we multiply both sides, left side and the right side, by this. If we multiply this by this expression, this from numerator cancels with this from denominator, and so we have x plus 6 in the numerator. Everything in the denominator cancels and only we have numerator, which is x plus 6. So in the left we have only x plus 6. What about the right side? When we multiply this in this bracket, first we multiply this in the first fraction. X with x cancels and then we have a times x plus 3. Then we multiply this in the second fraction. When we multiply this in this fraction, x plus 3 with x plus 3 cancels, so we have only bx. If we multiply a in the bracket, then we have x plus 6 equals ax plus 3a plus bx. If you pay attention, this term and this term, these two terms have x in common. So we can factor x from these two terms. And then we have x plus 6 equals a plus b times x. And then we have these 3a. Now, we compare the left side with the right side. And we equate the coefficient of x in the left side, which is 1, with coefficient of x in the other side. And we equate the constant in the left side with the constant in the right side. This is the way that we can find a and b. So, now we have this. Coefficient of x in the left side is 1, but coefficient of x in the other side, in the right side, is a plus b. The constant in the left side is 6. The constant term in the right side is 3a. Now, from this equation, simply we have a equals 2. Now that we have the value of a, we plug in 2 in the other equation, in this equation, and then we have 2 plus b equals 1, so b from here is -1, and a is 2. Now that we have the values of the coefficient, we substitute these values in the partial fraction. A is 2, so we have 2 over x plus b is -1, so we have -1 over x plus 3. So for this function we can write this as 2 over x plus -1 over x plus 3 dx. Finding the integral of these fractions is very simple. Let me remind you a formula from integral formulas. Integral of du over u is ln of u, or ln of absolute of u, plus c. We have this basic formula in integration formulas. Here we have 2 over x. 2 is a constant, so we can think 2 over x as 2 times 1 over x. What is integral of 1 over x? Based on this formula, integral of 1 over x is simply ln of x. You should be familiar with this probably. So integral of 2 over x is simply 2 ln of x. What about the other integral? Integral of -1 over x plus 3. Again, -1 is a constant, so focus on this, 1 over x plus 3. The negative is just a coefficient. Integral of 1 over x plus 3 dx is ln of the denominator, is ln of x plus 3. So similar to 2 over x, which was the integral was 2 ln of x, integral of -1 over ln of -1 over x plus 3, the integral is negative. Why we have to put negative? Because we have a -1 in the numerator, so we have -1 or negative ln of x plus 3. And if you want, you can put absolute for x and x plus 3. So it's better to put absolute here and absolute for x plus 3. And don't forget to put the constant at the end. So finally, integral of this function is 2 ln of x minus ln of absolute of x plus 3 plus c. Sometimes it's not a bad idea to rewrite your answer in a shorter form. Please pay attention to this. If you remember, we had this property for logarithmic functions, that if we have a power here, if we have a power for the expression, we can bring it down in front. Now we have a coefficient for ln, so we can move it back to the numerator, to the power. So what we can do with this? We can write ln of absolute of x times 2 in this form. We can write it as ln of absolute of x to the 2, or absolute of x to the 2. And because x to the 2 is positive, you don't need to put absolute anymore, but it's okay to leave it like that. Minus ln of absolute of x plus 3 plus c. Let me remind you another formula that sometimes can help you to write your answer in a shorter form. ln of a minus ln of b is ln of a over b. If we use this for here, this is our a, this is our b, so we can merge these two ln and write it as a single ln. So basically, let me erase here. We can write our answer, we can write this in this form. So our answer can be written as ln of absolute of x to the 2 over x plus 3 plus c. Attention, what happened? This goes in numerator and this one goes in the denominator based on the property of ln or logarithmic functions. But this step is optional, but sometimes it can be helpful, especially when we have definite integrals. Let's take a look at the next example. Here we want to find the integral of 1 over x to the 3 plus x. This is a little harder example because we have x to the 3 in the denominator compared to the previous example which we had only x to the 2. So again, we start by factoring the denominator. So we have 1 over x3 plus x, which we can write it as 1 over, if we factor x, then we have x to the 2 plus 1. we have two factors in the denominator, x and x to the 2 plus 1. For x, we just simply put a here. But attention, this is a quadratic expression and it is irreducible. What I mean by irreducible? Irreducible is a quadratic that we cannot factor anymore. You cannot factor x to the 2 plus 1 anymore. So, because it's a quadratic that is irreducible, if you remember from my other videos about quadratics that are irreducible, for numerator it's a bad mistake to just simply put b in numerator. When you have a quadratic in the bottom, in the denominator, numerator should be linear, which is in this form, bx plus c. If we had another quadratic in the denominator which is irreducible, then we have to add dx plus e, and so on. So because the denominator is degree 2, numerator is degree 1. Pay attention to this. What is the degree of denominator here? 1, because x to the 1. Numerator is a constant. Why a constant is in the numerator? Because the degree of numerator should be less than the denominator, and degree of a constant is 0. So the degree of numerator is less than 0, less than the denominator. Here we have three unknowns, a, b, c. Similar to the previous one, it's not really hard to find a, b, c. We are going to multiply left side and the right side by x times x to the 2 plus 1. So we multiply left side and the right side by this to get rid of denominators. If we multiply left side by this completely cancels the denominator, and in the left side only we have 1. But what about the other side? What about the right side? In the right side, when we multiply this expression, x from numerator with x from denominator cancels, and then we have a times x to the 2 plus 1. And when we multiply this in the second fraction, this cancels with this, and then we have bx plus c times x. If you want to get more familiar with this technique with finding coefficients and stuff like that, please watch my other videos about partial fraction decomposition. Now, for finding ABC, we distribute the brackets. So we have 1 in the left side, simply 1. Then we have a, what is this? Is this a? No, it's not a. So ax2 plus a plus bx2 plus cx. Now, in the right side, we start factoring similar term. If we attention, we have two terms with x to the 2. So we combine these two and we factor x to the 2 from them. So basically we have a plus b times x to the 2. Then we have only cx. And at the end we put the constant a. Now let us start comparing left side with the right side. In the left side, what is coefficient of x to the 2? Do we have any x to the 2 here? No, I can't see any x to the 2. So the coefficient of x to the 2 in the left side is 0. What is coefficient of x to the 2 in the other side? A plus b. So a plus b is 0. Easy. Now compare coefficient of x in the right side with the left side. Again, in the left side we don't have any x, but in the right side we have cx. So c is, yes, 0. In the right side we have a constant a, in the left side we have constant 1. So a is 1. Now that we know a is 1, look at the first equation. A plus b is 0. So we plug in 1 for a. So from here 1 plus b is 0. And so from this b is negative 1. We know all the values, all the coefficients. So let's substitute that here. So we have integral of a is 1. So 1 over x. We plug in 1 here. 1 over x plus bx. B is negative 1. Negative x plus negative x, but c is 0, so plus 0 makes no sense. Just put negative x over x to the 2 plus 1 and dx. From previous example, we know that integral of 1 over x is ln of x. This is a very simple formula. Ln of absolute of x is better to write. But what about negative x over x to the 2 plus 1? What is integral of this rational expression. Okay, let's focus on this a little more. Negative x over x to the 2 plus 1 dx. Let's focus on this. And let me teach you something here that can help you to do these type of questions faster. Here, for finding this integral, you have to do a simple u substitution. And the method basically is this. You suppose the denominator to be u, then you are going to find du, and so on. But is this really the best way to find this particular integral? Not really. You should be able to find integrals like this, which we will see in partial fractions a lot, very fast, in maybe 5 seconds. Please pay attention. We know we have this formula. Integral of du over u is ln of u. You are familiar with this formula. But what is really this formula? Tells us. If something, u can be anything. It can be this expression. When something is in the denominator, if derivative of that expression is numerator, du, derivative of u, it's differential of u, but you can consider as derivative of u. If something is in the denominator and its derivative is exactly in the numerator, then the integral of that expression is ln of u. Let me repeat this again here. When some expression is in the denominator and its derivative is exactly in numerator, the answer of integral is simply ln of u. You don't need to do u substitution and waste your time for that. Let me show you some examples how this works. For example, suppose you have this. What is integral of 3x to the 2 over x to the 3 plus 5 dx. I notice that derivative of x to the 3 plus 5 is exactly 3x to the 2. So the answer of this integral is ln of x to the 3 plus 5. Of course, if you want to put absolute, it's okay, and that's it. As you can see, it doesn't take so much time. You don't need to choose u as the bottom, then take derivative, substitute back, and so on. Another example. Suppose we want to find this integral. Integral of cosine x over 2 plus sine of x dx. What is this integral? What is the derivative of this expression? Exactly cosine of x. Derivative of the denominator is exactly in the numerator. So the answer of this integral is ln of the denominator, ln of 2 plus sine of x. So as you can see, it's a very fast method. But sometimes we have the derivative of the denominator in numerator, but not exactly, with a little difference, with a coefficient difference. Let me show you an example. Suppose we want to find this integral. Integral of x over x to the 4 plus 9. x3 here and that's it. This is the question. What is derivative of the denominator? Derivative of x to the 4 is 4x to the 3. But we don't have 4x to the 3 in the numerator. Simply you can multiply numerator by 4. Now you have 4x to the 3. But because you multiplied, it's not part of the question. 4 was something that you multiplied in numerator. You have to put the reciprocal in the outside to cancel the effect. So we multiply numerator by 4 and we multiply the reciprocal in the outside to make it cancel its effect. Now, what is the derivative of the denominator? Exactly this. So the answer of this integral is again ln of the denominator. And of course, don't forget to put this 1 over 4 outside of your answer. Now finally, I think you learned the method. Back to our question. What is the derivative of x to the 2 plus 1? 2x. But unfortunately, we don't have 2x exactly in numerator. We have x, but that negative is extra. First of all, don't worry for that negative. You can put that negative outside. So focus on this. What is the derivative of the denominator? 2x. When you look at the numerator, you notice, okay, x is there. And multiplying just a constant, not anything, just a constant, a number in numerator, and multiplying the reciprocal of that in the outside is completely fine in any integral. So we multiply 2 in the numerator when we put 1/2 outside. So don't make this mistake to multiply, for example, numerator by x or radical x or sine of x. No, you are not allowed to do that. Just a number you can multiply and the reciprocal outside. Now, the answer of this integral is negative 1/2 because it's negative 1/2 outside. The derivative of the bottom is exactly in the top. So the answer is ln of x to the 2 plus 1 plus c. So the answer of this integral is negative 1/2 ln of x to the 2 plus 1. So back to this question, the answer is negative 1/2 ln of, if you want you can put absolute, but it's not really necessary because x to the 2 plus 1 is always positive, but I am going to put the absolute anyway, although it's not really necessary. Before we jump to the next question, let me show you how you can merge these two ln together and make it one single ln. First, let's get rid of this 1/2 here. We move that to the power. So we can write this answer in the form of ln of absolute of x minus ln of x2 plus 1 to the 1/2. But we know that when something raises to the power of 1/2, it means that it's a radical. So you can write it in this form as well. Or write it as something, a bracket to the 1/2. But this is definitely better form. Now we have 2 ln and a negative between. Similar to the previous question, we can write it like a division. So the final answer for this question is, basically we can write finally this in this form. ln of absolute x over radical x2 plus 1 plus c. Let's go to the next example, and basically our final example in this video. In this example, in the denominator again we have x to the 3, so this is going to be a little challenging question again. And so it seems similar to the previous question. And maybe you think we have to factor the denominator and then write the partial fraction decomposition. Yes, but first, before doing that, we have to do something. Can you guess what is that? Yes, the degree of numerator is exactly equal to the degree of denominator. In numerator we have x to the 3, and in the denominator also we have x to the 3. And we know that when the degree of numerator is greater than or equal to the degree of denominator, first we have to do a long division. You can write the partial fraction decomposition only when the degree of numerator is less than the degree of denominator. So here, first we have to do the long division. Let me show you how we can do that. Maybe you don't remember long division so much. We want to divide this by x to the 3 plus x to the 2. X to the 3 divided by x to the 3 is 1, so we put 1 here. We multiply that 1 in this expression and then we get x to the 3 plus x to the 2. Very simple. Now we have to subtract this from this. Here it's very simple, subtracting these two from each other. But if it was a little confusing for you, you can change the sign of these expressions, and then instead of subtracting, you can add these with these. So it's up to you. Anyway, subtract any way you like. So x3 minus x3 would be 0. Then 4x to the 2 minus x to the 2 would be 3x to the 2. And don't forget to put x minus 1. Now this expression, the degree is 2. But the degree of this polynomial is 3. So the degree of the remainder is less than here. So we are not going to continue the division because we can't continue the division, and that's it. So for this function we have this equals to 1 plus 3x to the 2 plus x minus 1 all over x3 plus x2 dx. And because I want to do the calculation here, let me erase this from here. Before I start writing the partial fraction decomposition form for this, let me show you something. How we can rewrite this in this form maybe a little faster without line division. We have x to the 3 plus 4x to the 2 plus x minus 1 over x to the 3 plus x to the 2. What we want to do here, we want to get rid of this x to the 3. To get rid of that, I am going to make the numerator similar to this. I have x to the 3 exactly in numerator, but I need x to the 2. So I am going to write this 4x to the 2 as x to the 2 plus 3x to the 2, because x to the 2 plus 3x to the 2 is exactly 4x to the 2. So nothing wrong is with my algebra here. I can do this, and it completely makes sense. Now, we are going to group these two together. We consider this as a group. And if we divide this by this, x to the 3 plus x2 over x to the 3 plus x2, it would be exactly 1. And then, look at this. This is exactly what we had here. So, by dividing numerator by denominator, we can get the same answer without line division. But line division was not so complicated. So, it's completely up to you. Which method do you prefer to do? Now, let us start the process for partial fractions. So, we want to write 3x to the 2 plus x minus 1 in terms of partial fractions, in terms of simpler fractions basically. First we factor x to the 2 and then we have x plus 1, and in the numerator we have 3x to the 2 plus x minus 1. How many fractions we need here? 3. X, x2 and x plus 1 at the end. Maybe you wonder why 3? Because x to the 2 is a repeated linear factor. X to the 2 is x times x. And because it's a repeated linear factor, we have to put 2 partial fractions for that. If it was x to the 3, we had to put x, x2 and x3, 3 separate fractions. And if it was x to the 10, 10 different fractions for that. So this is different than irreducible quadratic factors. Irreducible is when we cannot factor, but you can factor x to the 2 because x to the 2 is x times x. And for repeated linear factors, we have to put corresponding partial fractions. So for x to the 2, we are going to put 1x and 1x to the 2, separate fractions, and a, b, and c in the top. If again you struggle with writing the partial fraction decomposition, please watch my other videos in this regard to get familiar. This is not really challenging. Okay, we have ABC, and for finding ABC, again we are going to multiply left side and the right side by that big denominator x2 times x plus 1. So we multiply left side and the right side by this. When we multiply left side by that, we are going to get 3x to the 2 plus x minus 1. And when we multiply right side, first we multiply this in this fraction. X with 1x from here cancels, 1x remains here, don't forget. So what we have in the right side, we have ax times x plus 1. Then we have, for the next one, when we multiply x2 times x plus 1 in b over x to the 2, x2 and x2 cancels, and what remains for b? We have b times x plus 1, and for c, we have cx to the 2. Now we expand these brackets to find ABC. We have 3x to the 2 plus x minus 1 equals ax to the 2 plus ax plus bx plus b plus cx to the 2. If we factor similar terms in the right side, attention, this ax to the 2 and cx to the 2, we can factor x to the 2, and then we have a plus c times x to the 2. Then we have a plus b times x and b at the end. The reason that we do this is that we want to compare coefficient of x to the 2, x, and the constant with the other side. So we have to do this. Now compare the left side with the right side. By comparing left side and the right side, let's first compare the constant with the constant. What is constant term in the left side? -1. What is the constant term in the right side? b. So b is -1. Now let's compare coefficient of x with coefficient of x. A plus b is 1. A plus b is 1. Because a plus b is 1 and we know that b is -1, if we substitute -1 for b, then we have a minus 1 is 1, and so a is 2. So we plug in this value for b here, then we have a minus 1 is 1, so a is 2. So now we know the value of a, the value of b, and finally we want to find the value of c. A plus c is 3. This coefficient and this coefficient should be equal to each other. A is 2, so what is c? C equals 1. Now that we have all the coefficients, we can substitute and then we can integrate. So fortunately we have enough space here. Let me write my answer here. So finally we have 1 plus a, what was a? 2. So 2 over x. B is -1, so -1 over x. -1 over x to the 2. X to the 2. And finally c is 1. So 1 over x plus 1 dx. And finding the integral of these terms is really simple. What is integral of 1? Integral of 1 is simply x. Integral of 2 over x is 2 ln of x, or ln of absolute of x. For -1 over x to the 2, if you remember from derivative formulas, derivative of 1 over x is exactly -1 over x to the 2. So integral of -1 over x to the 2 is 1 over x. But if you don't remember this, how you can integrate -1 over x to the 2? For finding integral of -x to the 2, you can write it as -x to the -2. You can move x to the 2 to the numerator and write it this way. Now use the power rule in the integral to find this integral. This equals to -x to the power of, add 1 to the power, so it will be -1 all over -1 plus c. This negative and this cancels. So you have x to the -1, which is 1 over x. So integral of x to the -1 over x to the 2 is exactly 1 over x. And finally, what is integral of 1 over x plus 1? Integral of 1 over x plus 1 is, let me write it here, plus ln of x plus 1 plus c at the end. And this is the answer of this integral. I hope you liked this video, and by watching this video you have learned a little more about finding integrals with partial fraction decomposition method. If you like this video, please subscribe in my channel. It helps this channel to grow. See you in the next videos.